This is a screen recording of the solutions to the Forrest homework problems, which were assigned and due on December 2nd. At any rate, the first one was just asking about what's the weight of an elephant on Earth. So it's m times g. That's a version of Newton's second law, because weight is a force equals mass, and g is acceleration due to gravity. So it's 58,800 newtons on Earth. On the moon, you have the same mass, but it said gravity was 1/6 as strong, so I just took the total divided by 6, and I'm back to 9,800 newtons. Excuse me. Problem 2 was asking about the force at the highest acceleration. First of all, that's a ridiculous acceleration. I can't believe someone would survive, but whatever. And so when you want to find the net force, you need to find the total mass times the acceleration. Well, that's the mass of the person plus the mass of the sled, or the car, I guess. Rocket sled. And so we have to have the total mass. So that's 177 kilograms times 450 meters per second squared. And so that's 79,600 newtons. For P3, it was essentially a person, Sophia, whose mass was 652 kilograms and experienced a net force of 1,800 newtons. So you asked to figure out the acceleration, 34.6 meters per second squared. That actually is pretty high, but it's typical of some of the more extreme roller coasters. 4, the key with, I think we went over that in class. So basically the net force we find out, this was my free body diagram. The mass, we just take the gravitational force, or the weight, divided by 9.8, and I got 31 kilograms. And then the last part of this was just finding acceleration, and that's force over mass. For number 5 here, this was a bit sneaky. And so the key thing with this, I think, is to draw a free body diagram. So even though it didn't ask you to do that. And essentially, here is someone's like jumping out of an airplane. You've got the mass, you've got air resistance, so the acceleration is due to the net force over the mass. So you want to find out the gravitational force. That's 808.5 newtons. That and the drag, or the air resistance, are acting opposite directions, so we subtract the forces, and that gets you the acceleration. The faster and faster you go, the more the drag is, and so your acceleration would actually decrease. For P6, this was similar to the last one with P5. And again, this one did not say to do a free body diagram. This one actually did. But if I think about the thrust is upward, gravity is downward, I know the mass of the rocket, I know the acceleration of the rocket. And so I find the gravitational force, 1.02 newtons down. If this is accelerating upwards at that rate, then I can figure out my net force is equal to the mass times that acceleration. Well, that net force is going to be 4.77 newtons, which is 45.9 times 0.104. However, that net force is going to equal thrust minus the gravitational force. So essentially, that is m times a, right there. Maybe I should point that out. We will make that green, that clear, and that a solid line. So that's the net force, 4.77 newtons. So the thrust minus the 1.02 newtons of weight, or gravitational force, would equal the net force. So the thrust has to be more than the weight of the object. P7, I think we did this one in class, drew the free body diagram. You do need to remember this formula for the coefficient of friction. Apparently this got cut off here, but that's okay. So we have 84 kilograms, 0.35, coefficient of friction acceleration of 1.2 meters per second squared. So the net force, M times A, is 101 newtons. The coefficient of friction is force of friction over the normal force, but the normal force is equal to the gravitational force, as you can tell, and that's 823 newtons. So therefore, the normal force is also 823 newtons. 0.35 times 823, 288 newtons. Net force here, force push minus force friction. (101 newtons), force push minus 288 newtons of friction. So that means the push has got to be more than 288 newtons. It's got to be 389 newtons. And then finally, I didn't assign this one, but I want you to look at it. Essentially, you've got a force down here because of the sign. How much? 422 newtons. So obviously, you need 422 newtons up to counteract that weight. However, these wires aren't going directly up. They're 34.5 degrees each from the horizontal. These two should be equal since they're at the same angle. Force up has got to equal force down. So essentially this tension, the vertical component of that tension, and the vertical component of that tension should equal the 422 newtons of gravity. So I like to say force up equals force down. Force down is 422 newtons. Force up, if this is T1, is at an angle, actually they're both T1s because they're the same tension, then this vertical component would be T1y. So that's T1 times the sine of 45 or 34.5 degrees, opposite over hypotenuse. But since there's two ropes pulling up, it's 2 times T1 sine 34.5 degrees. So anyway, sine of 34.5 degrees is 0.566. Multiply that by 2. We get that the tension in each string is 373 newtons. Interestingly enough, note that when these are at an angle, they each have 373 newtons. If they were pulling directly up, they would each have only half of this force down of 211 newtons. So the more of an angle you pull at, the greater the force has got to be to hold this sign up, because more of the force is acting sideways, pulling against each other, and less would be acting to hold up against gravity. So the most efficient you could do would be to pull this straight directly upward, but that's not what happens in this case. Anyhow, hope those help.